Okay, good morning everybody. Today we'll be touching on topic 6.2, Newton's law of gravitation. Okay, so before we start, just want to let you know of your end of year topics. It will be these 5 topics. We have already covered 1, 2, and we're doing 6 now, so another 2 more topics to go before your end of year exam. Alright, we have already learned about Newton's 3 laws. So this is the 4th law that Newton came up with. And some people call this the greatest scientific discovery, which is his universal law of gravitation. Now, what does the universal law of gravitation says? It says that the gravitational force between 2 point masses, so this object and this object here, 2 point masses, is proportional to their product. So if I multiply them together, and inversely proportional to the square of their separation. So normally it's up to you. You can always call the big mass M1, or rather you can call one mass M1 and you call the other mass M2. What I like to do is that, instead of writing M1, M2, I just say big M is the mass of the bigger object, small m is the mass of the smaller object, and then I use this equation here. Alright, now since it's proportional, okay, so what if the 2 masses are not point masses with no radii? What if it's something like the Earth, the Sun, the Moon, which is rather big, right? So they're definitely not point masses. Can this discovery still work? So Newton spent much time discovering integral calculus to prove that as long as it's a spherical symmetrical shell of mass m, it's as if all of its mass will be located at its center. So yes, we can still use this formula for bigger objects. We call this Newton's shell theorem. Okay, so since it's proportional, right? Force is proportional to big M small m over r squared. If I want to write it as F equals to something, that means there must be a constant. So what constant is that? That constant is what we call the universal gravitational constant. Alright, big G. By the way, when Newton discovered this, he didn't know what this big G, what was the size, what was the value of this big G. And it was only about over 100 years later that it was discovered by Cavendish. So it's quite interesting, right? That how scientists, when they discover or when they search on something, they may not know everything about what they're researching on. But as people, more and more scientists, or as different scientists around the world research on the same thing, they add on to what others have already researched on. And so it makes the research a bit more complete. So yeah, that's interesting, right? And this happens to today, where you can see different scientists around the world, they're constantly researching on the same thing, and then they just add on to what others are already doing or others have already done. Okay, so this formula here, F equals to gmm over r squared. Now, when I say the formula F equals to gmm over r squared, you need to know that this G we're talking about is big G. Okay? Because there are other formulas when we have learned, like for example, F equals to mg, that G would be small g. Alright, so gmm over r squared, big G, big M, small m over r squared. This formula can be found in your textbook, it can be found in your data booklet. Yeah. And this G, that constant, universal gravitational constant, is 6.67 times 10 power minus 11 newtons meter square per kg square. This constant here can be found in your data booklet. The first few pages of your data booklet, flip to it now. See, can you find it? Alright. Now when we come to examples for the videos, you will pause when we come to the examples, you attempt the question first, and once you're done attempting, then you unpause it so that you can see what the solution is. Okay? So when we come to these kind of questions, always highlight. They tell us that the mass of the Earth is this value. I'm going to highlight big M. They also give us the mass of the moon, so I'll highlight that. And they tell us that the distance, the mean distance between the Earth and the moon is this value here. Now this mean distance, I'm going to call that our R. Okay, so the first question asks us for gravitational force. What's the formula for gravitational force? Gmm over r squared. Do I know what's big G? Yes, I know. Do I know what's big M? Yes. Do I know what's small m? Yes. Do I know what's r? Yes. So fit that in, you get this answer. Easy. Now, try part B and part C also. So part B, they ask for the speed of the moon in its orbit about the Earth. Now when the moon is orbiting about the Earth, what do you notice about its motion? It's going in a circular motion, that's right. So since it's going in a circular motion, this tells me that there must be a force acting on the moon, right? And what is that force going to be? It's going to be towards the moon. This is the centripetal force. This centripetal force is also the gravitational force, right? So since they're equal to each other, I fit the values in. Centripetal force, since they're asking us for speed, which is v, will I use mv square over r, or will I use mr omega square? Asking for speed, right? So I'll use mv square over r. Now in the previous slide, we have already found out what the gravitational force is. So I'll fit that value in here. The mass is going to be the mass of the moon, because that's the moon, it's the moon that's moving, right? And then it's the radius between the moon and the Earth. So from here you can find out what V is. Now so far all my values are given in 3SF, right? So 3SF, my final answer must also be written to 3SF. Period. So note, please highlight, they tell you in days. Period is T. So what do? Since I know the velocity, and I know velocity would be displacement over time. What's the displacement? It's going in a circular motion, right? So the displacement will be the diameter, which is 2 pi r. So 2 pi r over, what's the time taken for it to go around the Earth? This time taken would be 1 period, right? Because the time taken for one orbit. So I already found out what V is from the previous slide. I know what R is. From here I can find out what T is. But T, what's the SI unit for T? Seconds, that's right. So once you have found your answer in seconds, but the question asks us in days. So you got to divide by 60 seconds to give us in minutes, divide by 60 minutes to give us in hours, divide by 24 hours to give us in days. Okay, we come to gravitational field strength. Gravitational field strength is our small g. So we have already seen this formula, W equals to mg, way in advance, long time ago. So if I have this guy here, and he is next, whether he's on the Earth or he's away from the Earth, we know that there's going to be a force acting on him, right? So our weight is a force. And what is this force that's acting on him? Your gravitational force. So if I say F equals to mg, but I know my force is gravitational force, I can fit, before that. Okay, so if I rearrange it, because I want to find out what gravitational field strength is, so I have G equals to F over M. But I know that this force here is my gravitational force. So I put the formula in. So I take my F out. Okay, so G equals to 1 over M times F. And then F is GMM over R square. These two M's can cancel away. So I end up getting this formula here. So write this in your notes. This can also be found in your data booklet. And this is important, alright? Now, what's the unit for G? Newton per kg or meters per second square. So remember there are two formulas, okay? Sorry, two units. Now, what about the force between two people? Any couples in our class? Okay, anyway. So, if these two people say their average distance from each other is 1 meter, right? Of course, normally if they really like each other, they'll be closer, right? But anyway, so what's the force between them? So I use F equals to GMM over R square. G is my gravitational constant. M, I fit 80 and 50 in. And the average distance between two of them, say it's 1 meters. Now notice that this value is so small because of your constant, which is the power minus 11. So the force between the two of them will be too small to have any significant effect, which is why we never ever talk about force between two people. But if it's between planets and the person, so if one of this is me, But this is the mass of the planet, which is very, very big, right? If it's for Earth, say if it's about 10 to the power of 24, something like that, then it becomes significant. Okay, so pause here and try example 2. Alright, now when I look at example 2, first thing I'll do, I'll highlight. They asked me to find gravitational field strength at a point between Earth and Moon that is right between their centers, right in the middle of their centers. So what I'm going to do, I'm going to draw it out. I have my Moon, I have my Earth, and then they tell us that the mass of the Earth is this value, the mass of the Moon is this value, and they tell me that the distance between them is this value. Okay, so distance between them, I put that out, is this value here. I want to know what's G right in the center. So I'm going to write down, I'm going to take note that I'm talking about this point here, right in the center. So I write down what's the mass of the Moon, the mass of the Earth, and I know that at the center there is going to be gravitational field strength acting towards the Earth. We call that, and gravitational field strength acting towards the Moon. Okay, so towards the Earth I call it GE, towards the Moon I call it GM. Now what is the distance between this point to the Earth? I'll have to take the distance, divide by 2. Okay, so with this, how to find gravitational field strength due to the Moon or towards the Moon? So GM over R square. Put the values in. You can get the answer out. What about towards the Earth? Same thing, I know what G is my constant. Then M, I'll use mass of the Earth. And then the distance will be the half the distance, okay? It will be distance from the center to the Earth. So I also get, now I get this answer. But I want to know what is the gravitational field strength at this point here. So if I have gravitational field strength towards the Moon and towards the Earth, and you can see that these two are different values, and since they're in opposite different directions, and this is a vector, right? So I have to take the bigger value minus the smaller value to give me the net value, which I know will be towards the Earth, because towards the Earth is greater, since the mass of the Earth is greater. Okay, now pause here and try example 3. So for example 3, what's your answer? D? Yes? Okay, now what is the answer D? So they tell us that there's a point between M, okay, no, sorry, not that they tell us, but we should know. Now they tell us that, that I have equal masses, but they are of different radii, and they are held d distance apart from one another. So now please take note that when I want to find gravitational field strength, remember for your G, when you have your G equals to big GM over R square, your this R is from the center of the mass. It should be from here to here, okay? Or to wherever, whichever position. But it's always from the center of the mass. It should be from the center of the mass. But right now, my question here is from the surface. Alright, which means that effectively I need to consider this part here. So I know that R on the right is greater than R on the left. Alright, and based on the previous question, we know that there will be some point over here where our G is going to be 0, because there will be G in this direction, there will also be G in that direction. So somewhere along this point here, our G is going to be 0, which tells me that if one point must be 0, if I look at options A and D, there is a point where my G is 0. B and C doesn't have that, so I will cross out B and C. Alright, then since my radius for the right hand side is greater than the radius for the left hand side, this tells us that, so see over here, if R is bigger, that means my G on the left hand side must be smaller. Sorry, G on the left hand side must be greater, right? Because our R is smaller. So look at this, G over here must be greater than the right hand side. So it cannot be such that my G on both sides are the same. Alright? So A is wrong. Okay, example 4. Pause here and try this out first. Okay, so now what does it tell us? It tells us that these two stars have got equal mass m of this value, and the planet is 6.0 times 10 power of 11 meters away from each star. So this distance here is 6.0 times 10 to the power 11 meters. They ask us to show G due to one star is this value. Okay, so how do we do that? So I write down the formula. G equals to Gm over R square. I know what capital G is. What's M? M is the mass of the star, right? So I know what that is. And what's the radius? The radius will be the distance between the planet and the star. So we just have to fit that in. You get the gravitational field strength at the planet due to the star. Now, why do I not consider the mass of the planet? Because I'm talking about G acting in this direction here. So when you talk about so it's purely due to the star, right? The mass of the star that exerts this gravitational field strength on me, rather on the planet. Okay, now part B. Part B asks us to find the resultant gravitational field strength. Now, remember, gravitational field strength is a vector. So since it's a vector, I can use a vector diagram, alright, which is that tail to head plus this vector here, this vector here, I'm going to bring it down, tail to head. Resultant vector is from first tail to last head, right, which is the same as the diagram that I've drawn over here. So if this is 34 degrees, I know that this is also going to be 34 degrees. What is this angle going to be? 180 minus 34 minus 34, 112 degrees, right? Now, I know that this value here is, what's this value? Let's go back. 3.7 times 10 power of minus 4. So this is 3.7? Yeah. 3.7 times 10 power of minus 4. Is it minus 4? Yeah. I want to know what's the resultant vector. How do I get that? You use your sine rule. So, if this is our G net, okay, and this is our G, right, due to one star. So G net over sine 120 equals to sine 34 over 3 times 10 power of 3.7 times 10 power of minus 4. So fit the values in, you can calculate that out. You get your G net, your resultant gravitational field strength to be 6.1 times 10 power minus 4 Newton per kg. Alright, now how does the graph of G against R look like? So as I go further away from the Earth, what is G going to be? Is G always 9.81? By now you should know that it's not, right? 9.81 is at the surface of the Earth. So at the surface of the Earth, this is our radius of the Earth. Now over here is the center, right? So this is where our R equals to 0 meters. Okay, so at the surface of the Earth is going to be 9.81. Now, according to G equals to Gm over R square, if this is a constant, so that tells us that G is proportional to 1 over R square, or it's inversely proportional. So since it's inversely proportional, you get a graph that looks like this. Alright. So please take note of this graph because sometimes they can ask you such questions for the MCQ. Now what about if I go towards the center of the Earth? So this is on page 262 of your textbook under the Nature of Science section. As we go towards the center of the Earth, into the core of the Earth, what is G going to be? So let's work that out, okay? What's the G value as we go into the Earth's core? So we know that when it's at the surface of the Earth, it's going to be inversely proportional to R square. So what about from the center of the Earth all the way to the Earth's surface? So first thing you need to know is that this blue part here that I've shaded, that is assuming I'm standing at this point here, all right? So that is the amount of mass that's going to be affecting the gravitational pull that's on me. So if I use this, do you notice that right now, G is still a constant, R is changing, R has changed, right? I'm changing R because R is going to be decreasing. But what about the mass? Previously, mass is constant because I'm talking about just the mass of the Earth. But now as I go towards the center of the core of the Earth, towards the center of the Earth, your mass is decreasing. So if I have two variables, I cannot work this out easily. I won't know what the graph is going to look like. I need to change it such that I only have one variable. So since my mass is changing, now what is mass going to be? So you know the formula, density equals to mass over volume, right? So the density of the Earth, we assume it to be constant. Now how do I find, so mass would be density times volume. How do I find the volume of the Earth? It's a sphere, right? So it's going to be 4 over 3 pi r cubed. So I fit this inside this part here. So I have G, okay, over r square, then times rho 4 over 3 pi r cubed. Then you can cancel away your r square, and you're left with 4 over 3 G rho pi r. 4 over 3 is a constant, G is a constant, density is a constant, density of the Earth, pi is also constant. So now you're left with G is proportional to R. So as you go towards the center of the Earth, your G is going to decrease. As your R decreases, your G will decrease. So you get a straight line like this. Okay? Alright, we'll stop here for today. Can you look at your worksheet, gravitation worksheet 1, and you can start attempting some of the questions there. To know which questions, look at the Google Classroom. I'll tell you which questions to do.